Glass is one of the most brittle materials on Earth. Drop it, and it shatters into 1,000 pieces. But in the world of high-end foldable smartphones, glass must do the impossible. It must bend, fold, and flex hundreds of thousands of times without failing. This is ultra-thin glass, or UTG. To make a material that is traditionally rigid behave like a piece of paper, engineers have had to rewrite the laws of glass manufacturing. At a thickness of just 30 to 100 micrometers, thinner than a human hair, this material defies our basic understanding of physics. Beneath the sleek surface of your foldable device lies a masterclass in structural engineering, a story that begins not with a factory, but with the molecular bonds of silicon dioxide. We are looking at a manufacturing process where a single speck of dust can ruin a $30,000 batch, and where precision is measured in the width of a single atom. To understand how we got here, we have to look at the brutal, high-temperature birth of a material that shouldn't exist. How do you make glass that doesn't break when you fold it? The answer lies in the fusion of extreme chemistry and mechanical alchemy. Let's dive into the assembly line of the future. Our journey begins with the selection of the substrate. This isn't your standard window glass. UTG requires a specialized recipe of high alumina silicate. Scientists mix purified silica sand with aluminum oxide and specialized alkali elements. This specific chemical cocktail is designed to create a tight molecular lattice, one that is capable of undergoing extreme stress. The raw materials are fed into a melting furnace, heating the mixture to temperatures exceeding 1,600 degrees Celsius, or nearly 3,000 degrees Fahrenheit. At this heat, the material is a glowing orange liquid, a molten soup where every impurity must be purged. To ensure the glass remains crystal clear, the furnace uses platinum-lined components, preventing any contamination from the furnace walls. Controlling the viscosity is critical. If the mixture is too thick, it won't flow, too thin, and it won't hold its shape during the drawing process. Every gram of the input is monitored by laser sensors to ensure the chemical balance is perfect, for even a 0.1% deviation can lead to catastrophic failure during the folding test weeks later. This is the foundation, the liquid fire that will soon become a flexible screen. The most critical stage in forming UTG is the fusion, or overflow downdraw process. Instead of pressing the glass into a mold, the molten liquid is pumped into a massive V-shaped platinum trough called an isopipe. The liquid glass fills the trough and overflows both sides, meeting at the bottom to form a single continuous sheet. Gravity is the primary tool here. As the glass flows down through the air, it isn't touched by any rollers or mechanical tools while it's still hot. This is vital because any contact with metal would create microscopic scratches that act as stress points, leading to cracks later on. As the sheet descends, pull rollers at the bottom gently stretch the glass thinner and thinner until it reaches its target thickness of roughly 30 to 70 micrometers. It's a delicate dance of thermal control and speed. If the rollers pull too fast, the glass snaps, too slow, and it becomes too thick to fold. The entire environment is a Class 100 cleanroom, where the air is filtered so thoroughly that there are fewer than 100 particles of dust per cubic foot. In this sterile vertical descent, the glass transitions from a liquid to a solid, perfectly flat and impossibly thin. Even at 30 micrometers, the glass is still too fragile. To make it tough, it must undergo a process called chemical strengthening through ion exchange. Imagine the surface of the glass as a crowded room. Currently, it's filled with small sodium ions. The glass is submerged in a pressurized, molten bath of potassium salt, heated to about 400 degrees Celsius. Through a process of diffusion, the smaller sodium ions leave the glass, and the larger potassium ions from the salt bath take their place. Because these potassium ions are much larger, they wedge themselves into the molecular gaps, creating a state of high compressive stress on the surface. This is essentially preloading the glass with pressure. When you bend the display, it has to overcome this internal compression before it can even begin to experience tension. It's like armor plating at the molecular level. This process increases the surface hardness and makes it significantly more resistant to scratches and impact. After several hours in the bath, the glass emerges with a structural integrity that belies its paper-thin profile, moving one step closer to your pocket. Now that we have a large, strengthened sheet of UTG, it needs to be cut into the shapes required for smartphones. But using a traditional diamond saw on something this thin would shatter it instantly. Instead, engineers use femtosecond lasers. These are ultra-short pulse lasers that fire in intervals of 1/4 of a second. The light is so intense and fast that it bypasses the heating phase. It essentially disintegrates the molecular bonds of the glass instantly without heating the surrounding area. This is known as cold ablation. By avoiding heat, the laser prevents microfissures or thermal stress from forming along the edges. After the laser provides the rough shape, the glass undergoes a specialized edge grinding process using chemical etching. We must ensure the edges are perfectly smooth. Even a microscopic jagged edge could become the starting point for a crack during a fold. These edges are polished until they are as smooth as the surface itself, ensuring that when you apply pressure to the screen, the stress is distributed evenly across the entire structure rather than concentrating on a single weak point. While UTG is incredibly tough against pressure, it is still glass. If a sharp object, like a grain of sand, hits it with enough force, it could still fracture. To solve this, manufacturers use a process called PET lamination. A high-strength, optically clear polymer layer is bonded to the top of the glass using a specialized pressure-sensitive adhesive, or PSA. This layer serves two purposes. First, it acts as a shatter shield. If the glass does break, the polymer keeps the shards in place. Second, it alters the flexibility curve of the glass, helping to manage the neutral axis. In engineering, the neutral axis is the area of a material that experiences zero stress during a bend. By carefully layering polymers of specific thicknesses on top of the UTG, engineers can shift this axis to ensure that the glass fibers are under as little tension as possible during a fold. This hybrid sandwich of hard glass and soft plastic gives us the best of both worlds: the premium feel and scratch resistance of glass with the durability and impact absorption of plastic. This lamination must be done in a vacuum to ensure zero air bubbles are trapped, because even one molecule of air would be visible to the user. Before a single screen leaves the factory, it must prove its worth in the torture chamber. Every batch of UTG is subjected to mechanical stress tests that simulate years of heavy use. Robotic arms fold and unfold the glass tens of thousands of times, usually aiming for a benchmark of 200,000 cycles. That is the equivalent of folding your phone 100 times a day for 5 years. They test the glass at extreme temperatures, from -20 degrees Celsius to over 60 degrees. This ensures that the adhesive doesn't fail and the glass doesn't become too brittle in the cold or too soft in the heat. Lasers and high-speed cameras monitor the surface for fatigue, looking for any sign of delamination or microscopic cracks. They also perform a ball drop test, where a steel sphere is dropped from a set height to measure impact resistance. If a single sheet fails, the entire production lot is discarded. This rigorous quality control is the only way to ensure that the bleeding-edge technology remains reliable in the hands of millions of consumers. It is the final gatekeeper in the journey from sand to a folding masterpiece. Ultra-thin glass is more than just a screen. It is a testament to what is possible when we push the boundaries of material science. What started as molten sand and alumina powder has been transformed through gravity-fed drawing, chemical ion exchange, and femtosecond laser precision to become a material that defies its own nature. It is hard, yet flexible, brittle, yet durable. It is the heart of the foldable revolution, allowing us to carry tablet-sized displays in our pockets. As manufacturing techniques continue to evolve, we are looking at even thinner glass, tighter fold radii, and perhaps one day, displays that can roll and stretch without limits. Every time you open your foldable device, you are witnessing the result of thousands of hours of engineering and the manipulation of matter at the molecular level. The impossible has become everyday. Glass, which we have used for millennia to hold liquids and look through windows, has finally learned how to bend. And this is only the beginning of the story of how it's built. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.